Hello, I'm Delaram, and today we're going to talk about threads in JVM and what is the operating system's role. So in Java runs inside a managed runtime environment called the Java Virtual Machine, and when we make threads in Java, we want to see how these threads are shown to the operating system. Is it visible to the operating system or not? And how it is handled. So we're going to start with a quick introduction, and then we're going to talk about threads a little bit and thread creation in the Java virtual machine, and about two types of threads: native Java threads and virtual Java threads. And then we're going to do a conclusion. So we're going to start with a quick introduction. What are we talking about? Throughout this presentation, we have 3 demos which will help us understand this presentation better. So a thread is the smallest unit of execution scheduled by the operating system. Traditionally, apps directly relied on operating system provided threads. That means when an app wanted to have a thread, it would ask the operating system directly for it to provide a thread, and the operating system would do so, and it would schedule it across CPU cores, and the scheduling would be in the hands of the operating system. But Java runs inside a managed runtime environment called the Java Virtual Machine, and JVM abstracts many OS level details from the programmer, and threads are one of them. So, how does JVM make threads, and are these threads visible to the operating system? This is the core of our discussion. Let's have an overview on threads. So, basically, we know this. A process may be single-threaded or multi-threaded. Single-threaded process means that there's only one thread running, and multi-threaded process means there are multiple threads. Threads have they share the code, data, and files of a process, but each one has a separate registers and separate stack. So they share code, data, files, and these are separate. What the kernel does in an operating system, it creates threads, it maintains thread control structures, it schedules threads on available CPU cores, and it performs context switching. Context switching is basically when we're running a thread and then we want to do another thread. This is called context switching. So we're switching between threads. The number of running threads at any given moment is smaller or equal to the number of CPU cores. So for example, my Mac has 10 CPU cores, and we're going to run this demo. It makes 50 threads, and they are running a while true. So basically they are using the CPU as much as they can. Let's run this demo. So these are my CPU cores. As you can see, all 10 of them are used 100%. That is what we expected since it's running a while loop. That means it's using the CPU constantly. These are each a thread that was created. As you can see, I made 50 threads, so we have 50 threads here, and each of them are using about 20% of CPU, as we expected, because we have 10 cores and 50 threads. 10 divided by 50 is 0.2, which means 20% of the CPU. Each one of them is using around 20% of the CPU. Now let's kill that one. Let's go. So, thread creation in the JVM. Basically, this is how we make a thread in Java. It looks like any other Java construct, but it's actually closely tied to the operating system. We're going to talk about native Java threads. So this is a native Java thread. New thread, just a simple thread. That is a native Java thread. Native threads have a one-to-one mapping model. That means that every one thread that we create in Java maps to one thread in the kernel, and that means the JVM creates an OS thread using native system calls, and these threads are actually scheduled by the OS scheduler. So that means these threads are completely real and they are fully visible to the kernel. this has some limitations, as you might have realized until now. It's time to run die like a dog.java, and we can guess what that does based on the name. I found this code from somebody in Stack Overflow. You can see it right here, and let's run it. So basically what it does is it makes threads. It keeps creating threads, and each thread just runs a for loop. It sleeps 1 second, wakes up, sleeps 1 second. That's what it does. So we just want to see how many native threads we can create. Let's run this. Let's see what happens. So we created 6,115 threads, and then we got this exception in thread main, out of memory error, unable to create native thread, possibly out of memory or process resource limits reached. Let's see what happened over here. This is what happened. We have 6,115 Java threads. That is terrible. And it died just like a dog. Let's see what these limitations were. We can't make as many threads as we want because the operating system imposes some limits on thread creation. The number of threads per process is limited. The total system threads are limited, and each thread has a limitation on the amount of memory it uses. And since these native Java threads are real operating system threads, Java can't create as many as it wants. But what if we want to create more? So threads are memory intensive, they're expensive to create, they're inefficient for I/O heavy work. We are wasting the kernel's valuable resources for threads that are mostly waiting or blocked. So the kernel has a limited memory, and it's very important to have some memory in the kernel. But when we create so many threads and these aren't doing much work, for example, they're doing I/O, they're just waiting, they're blocked. We're just wasting the resources the kernel has given us. But I want to make as many concurrent threads as I want. We have two choices here. We can use thread pools, or we can use Project Loom. Let's take a look into both. So thread pools. A thread pool is basically a fixed number of threads that we keep reusing. So the server creates a fixed number of threads, and then we have some incoming requests or tasks that they are in a queue. If any one of these threads, the threads are these squares and the circles are the tasks. So if any one of these threads in this thread pool is free, we can put a task, we can assign a task to it. And when that task is finished, it goes into the completed tasks, and a new task can take its place. So this still causes problems. This may fix the problem that you're not using the kernel's valuable resources anymore, but the problems is that blocking still blocks threads. If a thread comes here and it's doing I/O heavy work, it's still blocking a thread that is used in the kernel, when we could have replaced it with something else that is actually doing work instead of just waiting. And the second problem is, how many threads are we supposed to put in a pool? If we put too much, then we're just wasting the kernel's resources. If we put too little, we're going to have very little throughput. So what are we supposed to do? And this is where virtual Java threads come to the rescue. So virtual threads are introduced by Project Loom. These are lightweight threads that are entirely managed by the JVM. So they're not OS threads, and the OS doesn't see them. They're invisible to the OS. And they're scheduled by JVM instead of the kernel. So they're scheduled in user space instead of the kernel space. And the kernel can do whatever it wants, and JVM can do scheduling, and it can use some maybe better algorithms for scheduling these threads. These threads are run on top of a small pool of OS threads called carrier threads. So virtual threads have an M to N mapping model where M is usually much bigger than M. So we have M number of virtual threads and N carrier threads, and these M are mapped onto a fewer number of carrier threads. Let's see how that works. Let's take a look at another demo. So this demo is the virtual threads demo. We're going to start a virtual thread. So this is not a native thread, and it does the same thing. It just keeps sleeping for a little while and then wakes up. But the point is, we're going to make 50,000 virtual threads. So take into consideration that last time we wanted to make as many threads as we wanted, and we hit the limit on 6,115. Let's see what happens this time. Okay, so let's find the threads. As you can see, we have 9 threads. So there's probably a thread 0 somewhere, I have to find it. But then we only have 9 threads, and we've made 50,000 threads in virtual threads in this program. So we can see that the kernel's resources aren't used nearly as much as last time, because there's only 9 threads that are working here. Even though we have made 50,000 virtual threads, we can do 50,000 different tasks concurrently. So what's going on here? Look at this difference. What happens in virtual threads? So in traditional threading, blocking operation block an OS thread, but in virtual thread, JVM has the control of that. So when it sees that there's a blocking operation happening, it suspends that virtual thread, and instead on a carrier thread it throws another virtual thread that is actually doing work. So another virtual thread can run. This makes scalability, this causes scalability to go up, because we can create many more threads and just map them onto a small number of carrier threads, and whenever something is happening, whenever one of them is waiting, we can just switch it up with another thread that isn't waiting. So OS thread usage goes down. We save a lot of memory. As you can see, we only have 9 carrier threads over here. We had 6,115 kernel threads. That's a huge number. And we still have 44,885 threads more. So what OS does, it basically still does some scheduling, but it only does the scheduling on the carrier threads, and the main scheduling is happening in user space, and the JVM is managing the high level concurrency. Thank you for listening. I hope you learned more about JVM and how it creates threads. I would ask you to like and subscribe, but this is the first video I've made since 3rd grade, when I was creating a video for how to make a bracelet with rainbow loom. So this is only for extra credit. Thank you for listening. I'm happy that you've come this far. Like and subscribe and whatever. Bye.